Assalamualaikum warahmatullahi wabarakatuh and good day to all. In this lesson 11, we are going to look at chapter 7, Geometrical Optics. So geometrical optics has three subtopics, which is 7.1, 7.2 and 7.3, but in this lesson 11a, we are only going to cover 7.1 and 7.2. So from 7.1, we have 4 learning outcomes, which is the first one is state radius of curvature. So for radius of curvature, we use the letter capital R. So R is equal to 2F for spherical mirror. And B, sketch and use ray diagram with a minimum of 2 rays to determine the characteristic of image formed by spherical mirrors. And C, use mirror equations for real object only. And D, define and use magnification M. Okay, for 7.2, the refraction at a spherical surface, we only have one learning outcome, which is use this equation here for spherical surface. So what is geometrical optic actually? So to know that, what is light? Is light travel as a particle or does light travel as a wave? So actually, light has two properties or two characteristics. Firstly, as ray, and then secondly, as a wave. So as a particle or a ray or a light ray, so that is the section of geometrical optics. Whereas in the properties of light, where light is traveling as a wave, so that is physical optics. Okay, so geometrical optics, it is the study of light based on the assumption. So we have two assumptions here, which is number one, light travel in a fixed direction in a straight line as it passes through a uniform medium. And secondly, light, it changes the direction when it meets the surface of a different medium. Now, what is a spherical mirror? So a spherical mirror is a mirror with a curved reflecting surface. So for spherical mirror, it can be made of glass or any polished metal surfaces. So we have two types of spherical mirror, which is a concave mirror like this one, okay, where the reflecting surface is on the inside here, okay. This is the reflecting surface on the inside. So you assume that your eye will be around here, okay. This is your eyes, okay. So the reflecting surface is on the inside. And secondly, we have convex mirror, this one. So this is where the reflecting surface is on the outside here, okay. This is the reflecting surface of this convex mirror. So that are the two types of spherical mirror. And now we need to learn about the symbols that we are going to use. Firstly, we have C, capital C. Capital C is the center of curvature of the surface, the center of curvature. Okay, remember that this is a spherical mirror, a sphere. So we can draw an imaginary spherical like this, okay. And in a sphere, the center of a sphere is the center of curvature, okay. So here, this is the center of curvature, which is also called as, if you imagine it as a sphere, that is the center. And this is for the mirror, this is the center of curvature. We call it as capital C. And then for P, what is P? P is the center of the surface mirror, okay. Center of the surface mirror, P, right, this one. Which is for the mirror, what is the center? Which is between point A and B. Point A and B, the center of it is point P, okay. And then what is line CP? Line CP, CP here, okay. From C to P here, this is called as principal axis, or less commonly known as optical axis, okay. And next is AB. What is AB? So AB here is the aperture of the mirror. Aperture of the mirror. And then we have capital F. Capital F is known as the focal point or the focus, this one. and a small f is the focal length. So focal length is measured between from point F, the capital F, the focal point, to P, which is the center of the mirror. So this is called as the focal length, or small f. And lastly, we have the capital R, the radius of curvature, which is essentially the distance from point C to P. Okay, this is our R, capital R, radius of curvature. Now, for concave mirror, the focal point is defined as a point where the incident parallel rays converge after reflection on the mirror. Okay, let's look at this concave mirror. So we can see this is as the incident rays, and then it goes onto the mirror, and then it will be reflected. All the parallel rays will be reflected onto a single point, and that single point is called the focal point. Okay, and for convex mirror, it is defined as a point where the incident parallel rays seem to diverge from a point behind the mirror after reflection. Okay, so for these parallel incident rays, after it hits the mirror, it diverges in all sorts of direction. But actually, if you extrapolate lines behind the mirror, it all comes from a single point, which is point F here. And then this point F here is the focal point for convex mirror. Okay, now we have come to the first learning outcome of 7.1, which is we need to state the radius of curvature R is equal to 2F for spherical mirror. So what you need to do is you need to remember or use this formula. But how do we get this formula actually? Okay, so let's look at this explanation. Okay, a ray parallel to the principal axis is incident on the surface of a spherical mirror at point X. Okay, so for concave mirror, this is the incident ray. This incident ray is parallel to the principal axis. This is the principal axis. Okay, and then for convex mirror, this is the principal axis, and this incident ray for convex mirror is parallel to the principal axis. And these two parallel axes, these two incident ray, it hits the mirror at point X here. Okay, and then a radial line from the center of curvature through point X is normal to the mirror. Okay, so when we draw a line from the center of curvature to any point, okay, so that line must be normal to the mirror at that point. Okay, so this line is normal to the mirror at point X. Okay, same goes as this one. This one, we draw it from the center of curvature to point X, and at point X, this line would be normal to the mirror. Okay, and then what we have seen here is that the angle of incident is equal to the angle of reflection. Okay, so this is the angle of incidence, and this is the angle of reflection, and these two are the same goes as this one. This is the angle of incident, and this is the angle of reflection, and these two are the same. And by alternate interior angle is the Z. Remember the Z form. So this theta here is same as this one. So angle XCF is also equal to theta here. So XCF here is also equal to the angle here, right? And therefore, the triangle XFC is isosceles since it has two equal angles. This angle here and this angle here are the same. Therefore, we know that XF and FC are the same length. Alright? And then, since the incident ray is close to the principal axis, theta is small. Okay, we need to consider that this incident ray is very close to the principal axis, maybe like this here, and then when we draw the reflected ray, it will be something like this, very close. So we can imagine that xf, which is, let's say, imagine x is here, xf is equal to pf, and pf is equal to fc, and they are equal to small f, the focal length. Okay, then we know that r, which is measured from p to c, is fc plus pf, and then we know that pf is equal to small f, and fc is also equal to small f, and therefore our capital R radius of curvature is equal to 2 times small f, which is the focal length. Okay, B. Sketch and use ray diagram with a minimum of 2 rays to determine the characteristic of image formed by spherical mirrors. Okay, for ray 1, a ray is drawn from the top of the object parallel to the principal axis and is reflected through the focal point F. Okay, for concave mirror, we draw a parallel line to the principal axis, and then it hits the mirror, and then it will be reflected through the focal point F here. So from here, go to the mirror, it must pass through the focal point F, capital F. And then for convex mirror, from the top of the object, it hits the mirror, and then it will be reflected, but the origin must pass through the focal point F. Okay, that is our ray 1. From parallel to the principal axis, it must be reflected through the focal point F. Okay, for ray 2, a ray drawn from the top of the object through the focal point and is reflected parallel to the principal axis. Okay, this time we draw a ray from the top of the object passing through the focal point first, and then it hits the mirror. The reflected ray must be parallel to the principal axis. So like this. From here, through the focal point, reflected to the mirror must be parallel. Same goes for the convex mirror. From the top of the object, okay, go through the focal point. Okay, you need to extrapolate, elongate the line, and then the reflected ray is parallel to the principal axis. So that is our second ray. Our third ray is a ray drawn from the top of the object through the center of curvature and is reflected back along its incoming path. If you draw a ray from the top of the object through the center of curvature, it will go back where it came from. Okay, same goes as this one. From the top of the object through the center of curvature, it will go back to where it came from. So that is how we draw the ray diagram. We must use a minimum of 2 rays to determine the characteristic of the image formed by spherical mirrors. Okay, image formed by concave mirror. So first of all, U is the object distance, and ray diagram is what we will have after we draw the ray diagram. And what are the characteristics of the image form? Okay, so we have 6 cases, which is U, the object distance, is dependent on where it is. Okay, so for the case where U is greater than R is the radius of curvature. So what we will see, so this is the object. So firstly, we can draw an ray diagram that is parallel to the principal axis, and it must pass through the focal point. Secondly, we can draw using a ray that is passing through the center of curvature, then you will go back. Alright, and then so this is the top of the arrow, and so the point where these two lines intersect is the top of the arrow, but since this arrow is from the principal axis to the top of the arrow, so the image characteristic that we will get is real, and then inverted, it will be diminished. You see that this object is bigger than this one, so the image is smaller, the image is diminished, and the distance, or it is formed between point C and point F, between point C and F. Okay, so that is our first case. Second case is where the image is on the radius of curvature. Okay, so we draw the ray diagram. So must pass through the focal point, and then go through the focal point must be parallel to the principal axis. Okay, so that is the image form. So here we can see this is the top again, and then the image, this is the top of the image. Okay, and the characteristic is real. Okay, so why is it real? Because it is formed on the same side of the object. Okay, the image is inverted, it has the same size, and lastly it is formed at point C. Okay, our third case is where the object distance is between the focal length and the radius of curvature. So somewhere around there. So we draw the ray diagram for A1. Must be reflected through the focal point, then go through the focal point, must be reflected parallel to the principal axis. Okay, this you should not draw like this. Okay, just from this point here to where it intersect, it should intersect lah. Okay, so the image form is real, it is inverted again, and it is magnified. You can see that this object is smaller than the image. Okay, so the image is magnified, and it is formed at a distance greater than CP, greater than the radius of curvature. Okay, our fourth case is U is equal to F. U is on the focal point. Okay, so refracted must pass through the focal point, and then we draw a ray through the center of curvature, and then what we can see here, so actually we can have two outcomes, which is we can either have a real inverted, highly magnified and formed at infinity, which is we can have a, let's say we can have a image around here, but this is at infinity. Okay, so this image is real because it is formed on the same side. It is inverted. I'm sorry, this should be inverted. Okay, this should be inverted, and then it is highly magnified. It's very big, but at infinity. Or second case is you might get a virtual, which is formed at the back of the mirror, maybe around here, but this is formed at infinity as well, and this is upright and it is highly magnified. Okay. Okay, our fifth case is where the object distance is lesser than the focal length. Okay, so what happened? Alright, let's draw the ray diagram. So then we can extrapolate the line. So the point where these two rays intersect is the top of the image. So the characteristic that we get is we get a virtual image. Okay, and this image is upright. It is magnified. You can see that the image is bigger than the object, and it is formed at the back of the mirror. Okay, that's why we get a virtual image. And lastly, when the object is at infinity, what will happen is that you can see here the image is formed at F. Okay, so it is a real object, it is inverted, it is diminished. Okay, it becomes smaller and is formed at F, at the focal point. Now this is the summary of all the 6 cases of reflection for concave mirrors. Okay, look at here, this is the image, sorry, this is the object. So for, let's say, number 1, object 1, the image will be this one. Okay, for object 2, the image will be this one. Object 3, then image 3. Object 4, image 4. Object 5, image 5, and then also image 5, because case number 5 is where the image is formed at infinity, so it can either be real or virtual, but at infinity and highly magnified. And lastly, object 6. Okay, object 6, this is the image. Okay, virtual, magnified, then erect. Okay. So this is the summary of it. Now how about convex mirror? So for convex mirror, the outcome is only one. So the image characteristic will be virtual. You can see here, this is the object, this is the image. The image will be formed behind the mirror, okay, and then it will be upright, and then diminish, it becomes smaller and form at the back of the mirror. So only one case for convex mirror. So you can either remember it as, you can use this mnemonym here, VUD. So VUD, virtual upright diminish, only for convex mirror. Okay. Now, then outcome C. Use mirror equation 1 over f is equal to 1 over u plus 1 over v for real object only. And D, define and use magnification m is equal to height image over height of the object, or equal to negative v over u, where v is the image distance over u is the object distance. Okay, so for this spherical mirror equation, the first equation is this one, or we can substitute the value of f using this equation here that we have learned from learning outcome A, and then substitute. Therefore we get this equation, right? And then number 2, lateral magnification m. This is defined as the ratio between the image height to the object height. Hi, image over object, hi over ho, or equal to negative v over u. V is the image distance, u is the object distance. Okay, and then, so this is about magnification. If the modulus of m is bigger than 1, so we can see that the image is larger than the object. Then if the modulus of m is lesser than 1.0 or 1, the image is smaller than the object. Whereas if m is equal to 1, and then the image is the same size as the object. Right, and then for sign convention for spherical mirror, we will use a positive sign for the object distance u. If we have a real object and it is in front of the mirror, it will be positive. And then if we have a virtual object and it is behind the mirror, we will use a negative sign. And then for image distance v, if we have a real image, inverted image, and in front of the mirror, it will be a positive sign. And then if we have a virtual image, upright and behind the mirror, it will be a negative sign. Then for the magnification and height image, if we have an upright image and it is from behind the mirror, it will be positive, and it will be negative if it is inverted and it is formed in front of the mirror. For the radius of curvature, we use a positive sign for concave mirror and negative sign for convex mirror. And for focal length, the concave mirror will be positive, whereas convex mirror would be negative, right? So to make it easy for us to memorize, we can use this mnemonym, revu. If the image is real, it must be inverted, or if the image is inverted, it must be real. Whereas if the image is upright, it must be virtual. Okay, remember revu, real, inverted, virtual, upright. Okay, note, for a flat surface, the r, this should be a capital R, the radius of curvature is infinity. Okay, you cannot find this, the radius of curvature for a flat surface or a plane mirror. Okay, so for real image, what is a real image? It is one where the rays actually pass through the image, or is a location where the light actually convert and you can project real image on screen. Whereas for virtual image, it is one where the rays do not actually pass through the image. Okay, so the location from where the light appears to have converged. So this is the virtual image is formed behind the mirror, so light does not actually pass through the location, okay, and it cannot be formed on the screen. Okay, now for 7.2, refraction at spherical surface. So for this one, we only have one linear outcome, which is to use n1 over u plus n2 over v is equal to n2 minus n1 over r for spherical surface. Okay, so what is N1? So N1 is the refractive index of medium 1, right, which is it is medium that contain the incident ray, whereas N2, this is the refractive index of medium 2, where medium 2 is the medium that is containing the refracted ray. So we only need to use this equation. Okay, and then for convex spherical surface, our radius of curvature is positive, and then for concave spherical surface, our radius of curvature is negative, right? And the sign convention for refracting surface is for object distance u, it will be positive for real object and in front of the surface, and it will be negative if we have a virtual object and behind the surface. Whereas for image distance, it will be real behind the surface and inverted, and you will get a positive sign, and it will be a negative sign if the image is virtual in front of the surface and upright. And for the radius of curvature, it will be positive for convex surface and negative for concave surface. Right? Remember, review.